The second section will start soon. Please be seated. Now, welcome back all to the Sole Prize Lecture in Mathematical Science 2009. Now, after the intermission, we'll now invite our second speaker. May I first invite Professor Sun Kwok, Dean of Science, to introduce the speaker first. Professor Simon K. Donaldson will be our second speaker. Professor Kwok, please.
Yes, the second part of the Sole Prize Lecture will be given by Professor Simon Donaldson. And the topic of his talk is Old Themes and New Directions in Mathematical Aspects of Yang-Mills Theory. Professor Donaldson is currently a Royal Society's Research Professor of Pure Mathematics and President of the Institute for Mathematical Sciences in Imperial College London. He received his BA degree from Pembroke College, Cambridge University in 1979, and his PhD from Oxford University in 1983. His work in differential geometry and interactions with algebraic geometry and four-manifold topology. In 1986, he was elected as a Fellow of the Royal Society. He also received other honors, including the Junior Whitehead Prize in 1985, Field Medal in 1986, Crayford Prize in 1994, and King Faisal International Prize for Science in 2006. Professor Donaldson, please.
Well, thank you. It's wonderful to be here talking to you this morning. Let me say, you've had Cliff's fine lecture. You've had the jokes, the card tricks. This lecture's been a little bit more mathematical. Now you have to remember all those things you learned. But I hope not too much. And there'll obviously be a lot of overlap between what I'm talking about and what Cliff said, which I'll be able to refer to what he's told you already. The talk will come in four parts, is the plan. And so this first part, we're going to launch into an introductory section in which, so we're going to have to cover about 200 years of sort of, as it were, mathematics from about Newton till about the middle of the 19th century. So I have to get through that quickly. But let me begin just by talking about some general points about these sets, or we call them spaces, or more particularly manifolds of various different dimensions. So these things actually are not really at all mysterious why these things arise. They arise in all kinds of more day-to-day problems, perhaps sometimes we're not aware of. For example, a good example of a four-dimensional manifold is the set of straight lines in ordinary three-dimensional space. That set, in a natural way, is a four-dimensional manifold. So if we could think about the problem of, say, supposing we're trying to kick a football into a goal, as illustrated here. This is the goal. What we're trying to do, it's a simple model, is to find a line. The line we're going to project the ball along, so that taking into account of gravity and winds and everything else, it gets into the goal. But the problem in selecting how we're going to make our kick is to select a point in this four-dimensional manifold. So we're solving a question, perhaps unconsciously, in a four-dimensional manifold. And it'd be easy to write down many more such very down-to-earth examples where spaces of many dimensions come into play in all kinds of science and also daily life. There are two general things I want to say here. One is that we're trying to think about these perhaps rather difficult things of spaces of many dimensions. On the one hand, we can apply our geometric intuition based upon our understanding of, as it were, ordinary space. We can apply that in much more abstract situations, much more general situations. And I shall try to illustrate that later in the talk. So to an extent, what's the point to make is that what one sees in these more general situations is familiar. On the other hand, by contrast, quite new phenomena arise quite outside our day-to-day experience. So anyway, so let's press on with some classical mathematics. Let's talk about complex numbers. These are a very important way in which geometrical ideas enter in unexpected ways into mathematics. So the complex numbers have a two-dimensional number system. Any one is written as a real and imaginary part, I, the square root of minus 1. And the properties of the complex numbers are bound up, very much infinitely bound up, with special properties of the circle. If we take the unit circle, one thing we can see is that is what's called a group. To say by a group, we mean this is an algebraic structure where we know how to multiply two elements, and we have inverses and so on. So the special feature of the circle is it's a group with this multiplication just given by the multiplication of complex numbers. Or in fact, you could think of it the other way. You could think of it as the multiplication of complex numbers is essentially built out of this multiplication of this group structure excuse me, on the circle. Another feature of the circle, which is very important in complex variables, is the topology of the circle. So what I want to recall or mention is that the fact that if we consider a map, a continuous map from the circle into the punctured plane, or if you like, the complex numbers, but minus the origin, then such a map has what's called a winding number. We can determine an integer, possibly positive or negative, is the sense that the number of times that the circle is wrapped around the origin, or winds around the origin. So up or down here on the left, we have something of winding number 2. We go twice around the origin. On the right, we have something of winding number 0, although it sort of appears to somewhat go round the origin. In fact, it doesn't really wind round because we could pull that map, we could shrink it down to a point. So we have this topological notion of a winding number. And this is very important in perhaps surprising ways. If we could think, I'll put what's called the fundamental theorem of algebra. This is what says if we consider a polynomial, everything with complex numbers, p of z, it has some degree, some highest power of z that appears, then any such polynomial has a root. We can find a complex number, z0, such that p of z0 is equal to 0. So this is of course, wouldn't be true if we used real numbers. Precisely, we introduce the square root of -1, the basic imaginary number, because of the failure of that equation to have a real solution. So the way one can see this is to say, supposing this is 0. Supposing we didn't have a root. So whatever point z we take, here we get some p of z which is not equal to 0. So if I take a circle of some radius r, about the origin, then if I just look at the way this is mapped by p, I get a map from this circle into the plane minus the origin, just to exactly the kind we were considering before. So that thing has a winding number. Then we argue, if we took a very large circle, then essentially the important term is this term z to the d, and that would show us that the map has winding number d. And if I took a very small circle, then this center of that circle goes somewhere. This thing must map to another very small circle somewhere else, and that will have winding number 0. So supposing that there is no root, the winding number changes from d to 0 as the circle goes from very large to very small. On the other hand, because this winding number is a topological invariant, it can't suddenly jump, and we get a contradiction. Perhaps Gauss or somebody about that time. I said, so we're sort of going roughly from Newton till about 1860 in this quick. So we say the topology arises in an unexpected way when we're just considering questions of algebra with complex numbers. The other unexpected connections between complex numbers and mathematical physics, just of electromagnetism. If we take some complex numbers z1 up to zn, then we can write down this expression here, a function which is given by taking some multiple c1 over z minus z1 and then adding on similar terms. This is what's called a meromorphic function. It's not strictly a function because it's not defined at the special points when z is equal to one of the z1 up to zn. It has singularities there. It's called a meromorphic function with poles at these points. But exactly the same formula can be interpreted in a physical context as giving well, in fact, you can work with either the electric field or the magnetic field in this two-dimensional situation, which will be produced by point sources at these points z1 up to zn, where the C's will be where the strength of the sources, either, depending whether in the electric or magnetic situation, these would either be real or purely imaginary. So this is very simple to write down this formula in this case. But in more advanced questions introduced by Riemann, involving what are called Riemann surfaces, it turns out that the understanding the existence of generalizations of these meromorphic functions is a crucial issue. And this point of view of relations with electric and magnetic fields, that's to say, solutions of linear differential equations, is a crucial tool in proving general existence theorems, as was done by Riemann. So what I've tried to explain is that we have complex numbers bound up with the circle on the one hand, both the fact that the circle is a group and the topology of the circle, winding numbers. On the other hand, complex numbers connected to classical mathematical physics in a deep and important way. Now, what we want to talk about today really is four-dimensional geometry. And maybe the first person who perceived the special character of four-dimensional geometry was Sir William Hamilton. So after the introduction and great success of complex numbers, it was natural for mathematicians to look for yet higher dimensional number systems. And this was a problem that Hamilton was pondering in 1843. And well, he may have been pondering it for a while, but this is when he came upon the solution. He came upon a solution, inventing what we now call Quaternions. He hit upon this solution when he was out for a walk. So but he obviously didn't want to forget the answer. So most of us would maybe jot down the solution on a piece of paper in that situation, but perhaps he didn't have a piece of paper, so he jotted down the solution on a nearby bridge. He carved the formula defining these things into a bridge, lest he should forget it. And so what he would have carved would have been something along these lines. So the number, this is a four-dimensional number system. We have anything can be expressed. We have I, J, and K are the basic sort of generators, as well as the one. And there's some relations between these, which I've written down here. They have a high degree of symmetry between them, but let's not try to say too much about them. Anyway, this is the famous formula that Hamilton discovered and gives this four-dimensional number system of Quaternions, which to a certain extent generalizes complex numbers. Let me just say that Hamilton was very keen on his Quaternions and wrote lengthy tracts about them. Some 19th century mathematicians were not so keen, thought there were other superior ways of doing things, and indeed anything that you can do with Quaternions you could do in other notations if you like. So that's true also of what we're going to be discussing in the main part of the lecture here. For example, Cliff Taubes didn't mention Quaternions. I'm going to be saying they're the crucial thing. This is really, there are different ways you can express the same idea. Quaternions happen to be the way that fits in with the points I want to emphasize. In any case, one special fact is that just as the circle, let's say the one-dimensional sphere, is a group because of the structure of the complex numbers, so the three-dimensional sphere is also a group. We're thought of as the Quaternions of unit length in the natural way. And this also has special consequences for the group of rotations in four dimensions. If we take any dimension n, we can take Rn, that's to say the space of vectors with n entries, and talk about rotations of that space. So, for example, we call that SON. For example, SO2, we can represent these things by matrices. That would be given by these 2 by 2 matrices, which are probably familiar to many of you, involving you need to specify one angle, and you have a matrix, the angle of rotation, a matrix, given the cosines and sines. So, in fact, SO2 is just another name or a copy of our circle, again, as thought of as a group. We just have to specify the angle that we rotate through. And we could also again, express that in terms of complex numbers. But now if we go to 4 dimensions, what the existence of these Quaternions gives is a special decomposition of rotations in 4 dimensions. It turns out we can write any rotation in 4 dimensions. If we use Quaternion notation, identify vectors with Quaternions, we can write it as the map we get by taking a Quaternion Z to a product of Z with unit Quaternions, but because Quaternion multiplication is not commutative, as I should have emphasized that before, ij is equal to minus ji, not equal to ji. Because Quaternion multiplication is not commutative, we have a choice whether we do the product on the left or the right, and those give, in general, different things. And for the most, we should use both of those possibilities. So for any 2 unit Quaternions, u plus and u minus, we have a map we can write down in this form, and that thing gives a rotation, and up to let's just sign, which we'll ignore, those things, the rotations precisely correspond to the choice of these pairs of unit Quaternions. So up to a tiny subtlety, which we'll ignore, the space of rotations in 4 dimensions is actually the product of 2 copies of the 3-dimensional sphere. And this is a special phenomena unique to 4 dimensions. Nothing like it holds in any other dimension. There are a general context for talking about these kind of groups that we're talking about here, like the group of rotations, is what are called Lie groups. An important idea, which in the general context would be the idea of what's called the Lie algebra of a Lie group, but we'll only look at it in this particular case, is that of, as it were, not actual rotations, but infinitesimal rotations. And these things correspond to skew symmetric matrices. So I'm going to write lambda 2 of Rn is the usual notation for the space of skew symmetric n by n matrices. And the importance of these is that these can be thought of as defining infinitesimal rotations. That's to say, if I take a matrix M, and I consider 1 plus M, then the condition that's actually a rotation is that M plus M transpose plus M times N transpose is equal to 0. And if we're thinking of M as small, then we could think, well, we could more or less neglect the quadratic term. Then we would just get M plus M transposed is equal to 0. That's to say, M is a skew symmetric matrix. So it turns out there's a special property in 3 dimensions that we can identify the skew symmetric 3 by 3 matrices just with vectors. You see, the identification just goes in this way here. If we have 3 entries, v1, v2, v3 for our vector, we can make a skew symmetric matrix in the fashion shown, and that's the general one. But this is special to 3 dimensions. As you can see, if you just count the number of components you have for general n, the number of components in a skew-symmetric matrix is approximately a half n squared, which is much bigger than n. So this is, nothing like this can happen in general. The special thing which happens in 4 dimensions is that just as the rotations themselves could be decomposed into this pair of unit quaternions, so we can decompose the infinitesimal rotations into a corresponding pair of things. So we can write any skew-symmetric matrix in 4 dimensions as it were, a positive component and a negative component in a certain way that we could easily do explicitly. But this is just another manifestation of this special structures coming from the quaternions. So that was section 1. Lots of 19th century mathematics, complex numbers, quaternions, rotations, and so on. Section 2, I'll make an exertion into topology and try to explain both some of the ideas of, as it were, classical manifold topology as developed by Professor Smale, as Cliff mentioned, and many others, and the particular difficulties that arise in trying to apply these in 4 dimensions. So here, I want to return to the point on the first transparency, that there are some ways that we can profitably understand these higher dimensional spaces by analogy with what we're familiar with in ordinary space. We can use our geometric intuition. One fundamental principle of this kind, I want to emphasize, is the following, that if we have subsets P and Q of dimensions, let's call them little p and little q, and these are subsets inside some ambient space of dimension n, then if P plus Q is less than n, then a typical choice of such P and Q don't meet. Whereas if P plus Q is equal to n, then they will just meet in isolated points. If it's bigger, strictly bigger than n, then there may be a more complicated statement you could make. But these are the cases we want to say. So for example, again, if we just think about a pair of curves in 3-dimensional space, typically won't meet. Of course, you could take ones that do, but typical curves don't meet. And if you took some exceptional ones that did happen to meet, you could always move one a tiny amount to make it not meet. Whereas if you take, say, a curve and a surface, as illustrated here, in the 3-dimensional space, that's the case where P is 2 and Q is 1. The sum is the same as the dimension 3 of the space they're sitting in. So a curve and a surface will typically meet. If we see one picture like that, we can't move the curve or move the surface a tiny amount to get objects that don't meet. So what we want to discuss is how this idea interacts with what's called surgery, which is this operation of modifying manifolds by cutting them up, gluing them together in different ways, which Cliff talked about. So let's think about this as a sort of a model. Right down, we're talking about 2-dimensional manifolds, surfaces. So let's think about how we can, from the point of view of these surgeries, modify a torus, say, or donut, as Cliff described it, surface of a donut, to get a sphere. What you could do is you say, inside our torus, we find one of the basic loops that we obviously have, as we're calling it gamma here, going around the torus in a natural sense. And what we do is we cut along gamma. And now we've got an object with two pieces of boundary from the cut. And then we take ourselves a pair of standard disks, and then we glue these disks onto the two pieces of boundary that we made. So now we've got a new thing which doesn't have any boundary. And perhaps with the way we do it, it looks something like this in the picture. But that thing is equivalent in the topological sense to a sphere, because we can bend it out and flesh it out to make a nice round sphere. So this is a sort of simplest example of this fundamental process of surgery by which we can manipulate, in this case, two-dimensional manifolds, provided we could find this embedded circle, gamma, sitting inside our torus to begin with. Or we could apply the same idea to more general surfaces. So now we want to discuss doing the same kind of things in higher dimensions. And our second fundamental principle is this, that if we take a sphere of dimension p, SP, and a ball of dimension q plus 1, calling it bq plus 1, it's just a solid ball, and then we take the product of those two things, that's an object which has got some boundary, but the boundary of this thing is just the same as the boundary of a similar thing you get when you change the indices around a bit, as indicated here. So it's not hard to verify this by writing down formulae and so forth. And it's an example where we're generalizing to arbitrary dimensions a simple property that we can see explicitly in low-dimensional cases. So in this case, you see that the naught-dimensional sphere is just a pair of points. So this pair of disks that we were getting here, that would fit into this general story by taking a naught-dimensional sphere, the relevant formula. So the essential thing was that the boundary of what we got by taking a thin strip around gamma is the same as the boundary of these pair of disjoint disks. So this observation about these two different things having the same boundary means that we can extend our approach to higher dimensional situations, our approach to cutting up manifolds and making new manifolds out of them. So in particular, if we have a four-dimensional manifold and we find a two-dimensional sphere inside it, sigma, then, slightly oversimplifying, we could do one of these surgeries by cutting out a neighborhood of this two-dimensional sphere and gluing back the other thing, which has got the same boundary given by our little statement on the previous transparency. But that's supposing that we could find, if we could find these spheres, then life would be very simple, because we could take our sort of mystery four manifold, find this sphere, simplify it by doing one of these surgeries, and keep on doing that till eventually we get something very simple that we understood. But supposing we can't find this sphere, supposing in place of the sphere, we only find, say, a torus inside X, or T. Well, then we could say, well, let's try to, perhaps we just found this torus because we weren't looking for the right, we should try a bit harder to find a better object. So we could try to simplify this torus by doing a surgery inside X. So in other words, this is now we get a schematic picture. We would like to make the construction we were making before, but all inside X. So this is a schematic picture of, this is our four manifold. This is T, which is schematically our torus. This pair of dots is our gamma. And then the essential thing we need to do is to find these disks that we're going to glue in to do our surgery. So what we want to do is to find a two-dimensional disk inside our four-manifold, which has got boundary, this given circle, gamma, but apart from that shouldn't meet T. If we can do that, then we can do this surgery inside X to simplify T, to replace it by a sphere, and then we're in our good situation. But now we meet the crucial problem, which is just that 2 plus 2 is equal to 4. So if we consider D and T, those are each two-dimensional, but they're sitting inside this ambient four-dimensional thing. So we're just in the case where a typical D and a typical T will be expected to meet in isolated points. So although, roughly speaking, there's a whole theory of algebraic topology that could tell us whether we could find a D if we relax those conditions, we have no way of knowing we could find a D which doesn't meet T, or in fact there's another problem. We might have a disk which has got some self-intersections, because as in this indicated in this picture here, where two branches of this disk come across and meet each other. So this is the fundamental problem. I was going to explain, I think I shall omit it for lack of time, why just from that, on the basis of that formula we said for how things meet in different dimensions, that problem becomes less serious when you go to higher dimensions. When you go to higher dimensions, in fact, you have a bit of extra space, so you don't meet this same critical difficulty. But I won't take the time to explain that. So now we come to the central part of the talk, section 3, which is more about these special solutions of the Yang-Mills equations, or called it Yang-Mills instantons is what I will call them. So we want to consider a general Riemannian manifold, it's called. That's to say a manifold, but we have, so at each point in the manifold, we have the notion of a tangent vector, and calling it a Riemannian manifold just means we have a way of measuring the length of tangent vectors. So now, for each point, we have a space, right, as lambda 2 sub x, which is given by the infinitesimal rotations of the tangent space at x. Now, if we choose coordinates, then we could just identify that with the lambda 2 of Rn that we were discussing before. It would just be given by skew symmetric matrices. So the importance of these for this talk is that an electromagnetic field should really be best thought of as something which, for each point x on the manifold, gives us one of these infinitesimal rotations, an object of this lambda 2 x. See, the fact that, remember we said in 3 dimensions things are a bit special, so we could identify these things with vectors. That's why you don't really think of this, because you think of electromagnetic fields as being ordinary vectors because of that coincidence. But this is really how one should think of them. So in electromagnetism, we express this field in terms of a potential. So if we call the field F, so it will work in coordinates, so it's given by a skew-symmetric matrix, so it has entries Fij, and this potential expresses those Fij's in terms of derivatives of something called A, according by this formula that we have here. So remember we said that in 4 dimensions we had the special property that lambda2 of R4 could be decomposed into the product of positive and negative things. So in 4 dimensions we could write any electromagnetic field as a pair with a positive and a negative part in just the same way. So now we come to the generalization of electromagnetism called Yang-Mills theory. And the crucial thing is that this involves a Lie group, one of these Lie groups. But say we could think of this as, for example, it could be the 3-sphere, which we said is a group, or one of these SOMs for any M. Then we consider what's called a G bundle over our space X, which is, what this is giving for each point in X a copy of the group G. So we have a copy, we'll call it EX of G, but we're not to suppose that there's any preferred identification between EX and G. Then, in differential geometric terms, what we would consider is something called a connection on this G bundle. But it would take us perhaps too far afield to try to explain what that is. So I'll just explain things in terms of how the formulae would look in local coordinates in comparison with the case of electromagnetism. So the difference would be that, again, we're going to have a potential, sort of A, with indices, AI, and we're going to have a field, Fij, but now each of these things individually will lie in the Lie algebra of our group G. So essentially each of these things will be a matrix of some kind. And the formula relating them will be given by, where we start off with the same formula that we had before, involving the derivatives, but then we add on a quadratic term involving matrix multiplication of these A's. This is the characteristic feature of Yang-Mills theory. In fact, we recover electromagnetism precisely in the case when the group G is the circle. And in that case, because that's a commutative group, the relevant matrices commute, so this quadratic term that we add on is actually absent. So we recover exactly the traditional formula of electromagnetism. So it's been a great treat for me this week to have sat at dinner with Professor Yang, who will tell me about how he and Mills came upon this modification of electromagnetism and the need to incorporate this particular kind of quadratic term. So anyway, to press on, what we've now got, we've got a Yang-Mills field, which is one of these matrix versions of electromagnetism, but we're doing this in 4 dimensions, so we can make this decomposition into positive and negative pieces, which is specific to 4 dimensions. And finally, we call this object a Yang-Mills instanton if one of the components, let's say the positive component, is equal to 0. So that's quite a lot to understand and absorb. But really there are 2 main points to take away. First of all, this is if we think of this condition in terms of our A, our basic object, this is a nonlinear partial differential equation. It's a differential equation because it involves derivatives. It's nonlinear because we have that quadratic term involving matrix multiplication, which is precisely the difference from the classical case. And this is special to 4 dimensions because only in 4 dimensions do we have this decomposition of our skew symmetric matrices into positive and negative parts. Those are the key 2 points to take away from what we've said. So now, that's the instanton equation that we have on a 4-dimensional manifold once we've chosen one of these Riemannian metrics that tells us the lengths of tangent vectors. How do we use this to obtain the invariance of 4 manifolds, which Cliff Towers was discussing, things we can use in favorable cases to distinguish one 4 manifold from another one? So to explain this, let's go back to the fundamental theorem of algebra that we were discussing back at the beginning. We'll think about this in a slightly different way. So now we're thinking about this polynomial equation, P of z equals 0, where P has got degree d. The highest term is z to the d. So in fact, such an equation doesn't just have one root. It has, someone says it has d roots, is what one normally says, provided you count the roots with multiplicity in a suitable way, just as you talk about a quadratic equation having a double root, for example. And so a slightly different point of view on thinking about this, the fundamental theorem of algebra, is to think about deforming the polynomial. So we start with a polynomial, call it P0, our favorite polynomial which we understand, where particularly we understand all the solutions of the equation P0 of z is equal to 0. And then we can take our general polynomial P1 and deform it to P0 in an obvious way by varying the coefficients in a 1-parameter family, always keeping the same leading term. So the crucial idea is that as we vary the parameter t, the number of roots, if we count them in an appropriate way with multiplicity, stays the same. And we have our sort of initial situation. We have 3 roots here, say. We vary the polynomial. The roots vary, but they vary in a sense in a continuous fashion. So the number stays the same. Of course, 2 roots might come together and collide. Then we'd have to count them as a double root. But if we do that, we keep the bookkeeping, all works out, and the number of roots is the same. In particular, this is another way to prove that a general polynomial P1 has got d roots by deforming it to our familiar one. And this is a very important idea. We can apply this same idea not just to these polynomials with complex numbers, but to very general equations, say phi of x equals 0, where phi is some map from Rn to Rn. So an x is an n vector. So for very general equations, we can do just the same thing, but provided certain crucial properties hold, what we might call compactness properties. One thing we want is that we only have a finite number of roots. Supposing we had, of solutions of our equation, supposing we had an equation with an infinite number of solutions, keeping on going forever, that would be a different situation. Or we might have a situation where we only have a finite number, but as we do this deformation, one of the solutions gets lost, moves off to infinity, and then gets lost. That's a way in which we could start with, say, 4 solutions. When we make our deformation, we only have 3 solutions afterwards because one of them's got lost running off to infinity. In fact, we're thinking of higher dimensions, just the same ideas apply in one dimension, except there what you say is that you want to count this, the multiplicity you need to count solutions with could be, in general, be either plus or minus 1. So, for example, if you were considering kind of a cubic curve like this, a cubic one real variable, if you count these roots with plus, minus, plus, then you get the same answers when you deform the cubic to this case where you just have 1 plus. So this is a very general way of thinking about equations in many variables. And the same ideas apply to a large degree in infinite dimensions. In cases where typically, in the space of Rn, we have a space of functions of some kind, and in place of phi, we have a partial differential operator. So the relevant equation we'd be considering, like phi of x is 0, would now be precisely a partial differential equation. So if certain conditions are met, you can apply just the same techniques to such infinite dimensional problems and partial differential equations. I should say, Cliff mentioned that Professor Smale, one of the founders of this manifold theory we're discussing, is in the audience today. By chance, he's also one of the first people to point out this extension of these other kind of techniques to this setting of differential equations. So the basic requirements one needs are, first is what you have what's called an elliptic equation. Once you have that, then you can associate what's called an index to the problem, which is an integer, and we want to think about the case where this index is 0. Secondly, we want what's called compactness, which is precisely this question about solutions running away to infinity, or only having a finite number of solutions. So we want an analog of those properties to hold in our problem. If you have that, you have an elliptic equation of index 0, and you have some way of knowing you have this compactness, then you get a number by counting the solutions of your equation. And the crucial property is that this is essentially a topological invariant of the situation. It doesn't change if we make a deformation. If we deform some parameter, this number doesn't change. Now, these requirements are actually not often met. Particularly requirement 2 is not often met. There are many problems, say, arising in differential geometry, which lead to elliptic equations of index 0, but typically they won't have this compactness property, so we won't be able to follow through this approach to get an integer by counting the solutions. For example, we could consider the problem of what's called closed geodesics on a surface. So these roughly mean, if you think of our surface as a marble surface in space, these would be the equilibrium configurations of an elastic band stretched around your marble surface. So you might have one like this green one, say. But typically what happens is that you get infinitely many of these closed geodesics, infinitely many possible positions of your elastic band, but they get longer and longer and longer. So if you fix a given length, there's only a finite number of length less than that number, but because we can let the length get longer and longer and longer, we have infinitely many of these things getting more and more complicated, wrapping round and round in more and more complicated ways. So that would be an example of a problem where it doesn't make sense to count them because there are infinitely many, and we can't use this theory. And somehow that's the sort of typical situation that one encounters. Let's get to the punchline. The punchline is that we've found these special instanton equations, special form of Yang-Mills equations, building in properties of Lie groups and so forth. In a four-dimensional manifold, these are equations which satisfy these precious properties, and we can proceed to obtain invariance of the situation by counting the solutions. The crucial property of being independent of continuous parameters enters because to write down the equations we needed to choose this called Riemannian metric, a way to measure the lengths of tangent vectors, but the numbers we get don't depend upon that choice because we can always continuously vary from one choice of metric to another one. So I have a few more transparencies I'm now going to omit, in which I was going to say a bit more technical stuff about these instanton equations and why they satisfied this special property of compactness. But I'll omit that because my time is rapidly coming to an end, except to say it depends crucially upon topological properties of these Lie groups in connection with four dimensions via what's called the Chern-Weil theory. But that's rather more technical anyway, and we'll leave that out for lack of time. But let's see. We want to get to the conclusion somewhere. Just find. So now I want to sum up the main. Yeah, there we go. That's what I want. This is summing up then the main part of the talk. We saw there are special difficulties in four-dimensional topology to do with the propensity of pairs of surfaces in a four manifold to intersect in points, and the fact that we couldn't really control what these intersection points were. That's in one direction. In the other direction, B, we've seen there are special properties of four-dimensional geometry, going back to Hamilton and perhaps even further, connected to the Quaternions and such matters, which lead to this possibility of writing down these special instanton equations. So these things are related to some extent because we can see that these instanton invariants that we've been able to define using these equations tell us something about these special difficulties in four-dimensional topology. Essentially, they'd be telling us, if we translate it into the question about surfaces, they'd be saying that actually it's impossible to find a sphere, for example, or some statement of that kind. You can never remove these intersection points. But as Cliff Taubes has said, these instanton invariants don't solve all our problems in four-dimensional topology. They just perhaps give maybe just a glimmer of the real truth of the matter. And related to that, as it were, one doesn't see perhaps a fundamental reason for the connection between A and B. We see there is a connection because you can use one to help understand the answer to prove things about the other, but one doesn't see a clear and direct connection between the special properties of algebra of Quaternions and the fact that the three-sphere is a group and so forth, and these topological intersection properties. And it could well be that understanding in a more fundamental way the connection between these very different looking parts of mathematics could help to see the way forward in making further progress in understanding four-dimensional topology. So that, I think I will cancel section 4. Section 4 was going to talk about higher dimensions, some developments which are, in fact, somewhat connected to what are called the Cayley numbers, which are the final thing in the search to higher and higher dimensional number systems. But I will cancel that for lack of time and finish up.
Thank you very much. Welcome questions from the audience. Yes, Professor Mock. Yeah.
I understand the spirit of what you do is you use the number of instanton solutions to classify different topologies of four-dimensional space. Is that the sort of the main point? So why instanton equations? Are there other equations that could serve the same thing?
Well, we don't, I mean, there are certainly some. For example, these Seiberg-Witten equations, which Cliff mentioned, and connected to the pseudo-homomorphic curves, but essentially the answer is we don't know. There could well be, yeah, there could be some other equation which will help us to distinguish more four-dimensional manifolds, but we need somebody to discover this. To discover it. As I said, it's not as though just any old equation does the job for you. These equations have to have very particular favorable properties to be able to lead to topological information in this way. Which is
No, I asked this question because nature chose Maxwell's equations and generalized equations to describe the physical world. And those equations are the instanton equations. So